Welcome back to Computer Science 305. This is the last look at Prolog. This is part 2 of that lecture. So we're continuing on in problem space search, and we're now going to look at the 8 queens problem. So the 8 queen problem is basically it's played on a chessboard. It's with an 8x8 grid, and then we know that a queen can move to any number of spaces vertically, horizontally, or diagonally. 2 queens are in check if they are in the same row, column, or diagonal. In other words, so that if at any time a queen can move onto another queen's space, then it's invalid solution, right? So the problem here is we want to be able to place 8 queens on empty chessboards such that no queen can put another in check. And so we can represent this, right? We have we can represent a queen at a position. For example, 2-5 by using the predicate queen taking in xy. But it would be more readable if we use something more compact. So we know that there's no other pieces on the board, such as pawns or kings, and we'll end up just using a term of the form xy, right? We won't evaluate it as a quotient. We'll just have the term. So, for example, we have this chessboard configuration, right? We use the chessboard configuration as just a list of queens. For example, in what we have here, we see that this one is simply a 2-5, 3-7, 6-1, right? Except for we can see that the queen at 6-1 and the queen at 2-5 are in check. So thus, it's not a valid solution. All right, if we have that going on, the first step of this would be to initially we need to define a no check, which takes in a queen position and a list of queens, right? And it will succeed if and only if the xy queen holds none of the others in check, right? So let's go ahead and define this. We say no check. And then no check. So when we actually have a value, and a list, we can then say x. We're going to test whether x is equal to x1, or if y is equal to y1. And we then look at the absolute value of y1 minus y. We compare that. We check that it's not equal to the absolute value of x1 minus x. And then we say no check xy with a tail recursive call. Right? So this is, we'll walk through all of the items in the list, validate that it does not put any of the other items in check. Okay, save that, move along. So then we have legal for a list, right, will succeed if L is a legal placement of the queens and that all coordinates in range and no queen is in check. So we can really quickly define that to be legal, the empty, and legal xy, rest. We say legal rest member x. So now I have to check if x is within the range 1 through 8, 2, 3, 4, 5, 6, 7, 8, and whether member y is within the range 1 through 8 as well. And then finally, if all this is true, we have no check for xy rest, right? So once we have that, then we this is already enough to solve this problem. The query legal will find all legal configurations, right? So we can actually run this. We say consult queens, and then if we say legal x, it gives us the empty set, 1, 1, 1, 2, all the way through, right? and it will literally go all the way through trying to find all possible legal combinations. I'm going to kill it there. Now, we need to actually define, because we know that this is extremely long and it finds all 64 legal 1 queen solutions, then starts on the 2 queens, and so on. The problem is that we need to make it concentrate right away on the 8 queen solution. We would have to give it a different query, right? So something like we see above, or we see on this slide. So it'd be x is equal to underscore 2 7 8, right? And then we want to validate that they're legal. And we run that, and it gives me false. What is going on? What? Oh, sorry, that's my bad. It needs to be a capital X, not a lowercase x. And it will take a bit of time to solve that. Apparently not as much time as I thought. And we'll, every time we press the OR operator, it will look the semicolon. It will just create a new permutation of the existing solution that it gave us, right? So it gives us 8 4 7 2 as we see 6 7 5 3 4 6 3 8 2 5 and 1. And then everything beyond that is simply a permutation of that solution set. Then the solution will look something like we see here. Now, the problem here is it is very slow, and as I said before, it finds only the trivial permutations after the first one, right? It won't go and try to solve a new version of the solution, just gives us that existing one. So, but we do note that if we look at this, every solution has 1 queen in each column, and that's great. Solves the problem, right? 1 queen in each column, as we see here, and then 1 queen in each row, obviously, as we see there as well. Now, we can actually note that every solution can be written in a fixed order, as we see here, right? And then what this will do is it prevents it from continually looping through the same permutations, and will give us a way to define the goal term of a form that will restrict the search and thus speed it up while avoiding these any trivial permutations, right? Because you can't have that happen. So what we can do is we can create a new predicate called 8 queens, as we see here, right? Which then utilizes this understanding that we have to then create a better, the capability to find a better set of solutions. And then we just have to make sure they're legal, and we're good to go. Okay, so now if we go and run that, we have to make a slight update here. We don't need to actually manipulate the x and the x coordinates, right? Because we know they're good now. So we don't have to validate that the x's are not equal, because we can assume that they're distinct based on the modification we made to our actual solution. So we can get rid of this, and then we can also get rid of this because we know that x will always be a member of the set 1 through 8. So now we have that. And we can then run our 8 queens and get good results. So we'll save that change, we'll reconsult, and we'll go ahead and run 8 queens on just the variable x, and we get the initial solution shown there, and the next solution, the next one, all different solutions to solve that problem. So we could also, start manipulating this and we can actually take a look at the legal concept here, right? Is that we could define legal to instead have y constructed or checked that it's less than that it's greater than or equal to 1 and less than or equal to 8, right? Instead of just asking if it's a member of the list 1 through 8. And if we did that, we'd have to have y instantiated and then actually generate the value. We don't necessarily want to do that, mainly because it's probably not the best way of doing things, right? Mainly because if we were then to run legal here, we would have the arguments not sufficiently instantiated, right? Because legal rest condition must come first because it generates the partial solution tested by no check, right? So if we try to do no check and then legal, right, to maybe improve in our legal operation, would not work well because we want to get the tail recursion out of this. But unfortunately, we actually need legal to generate rest to use rest in no check. So it's not going to work out well. But anyway, so the 8 queens problem is a restricted version of the n queens problem, where you have an n by n board with n queens, which then becomes effectively an NP hard problem or NP complete problem as well, because it would take exponential time to try to figure out all possible solutions, right? So this is a really difficult problem. All right, now we're at the last part, right, where we say goodbye to Prolog and detect all the things that we did not look at. So when we are looking at Prolog, there's a few operators we didn't talk about, right? There's the arrow operator, or implication operator, which is for if-then and if-then-else operations. Then you also have the semicolon, which is for disjunction of goals. So, right, we had the comma, which is for conjunction or and the semicolon is for disjunction or. There's also exception handling in Prolog, right? We have the capability of throwing and catching both system-generated and user-generated exceptions. And there's also a small API. And there's also a bunch of, so the ISO API, which is the basic definition for what is included in Prolog, which most systems will provide along with far more. There's also lots of Prolog libraries that exist out there, so you can do IO, GUI, pretty much anything you really want. Prolog's been around for a really long time, so there's lots of code available for dealing with it. We also do need to note that, of course, it's a small language, so unlike in ML and Java, where we did not even cover, we barely scratched the surface of those languages. Prolog, we really, with the exclusion of the API, right? Because I mentioned at the very beginning of this class that I would not be spending time on APIs. We've covered almost all of the language, right? It's really small, but yet it's extremely powerful. It's extremely powerful. It's just not very easy to master. It's I think you could spend a large amount of time really sitting down and learning Prolog before you became what I would call a true master of this. But and then one of the most important things that we did skip was the techniques that programmers use to get the most out of it, right? So these would be, like, for example, patterns of programming programming in Prolog. We talked a lot about what I would call the patterns of ML, right? And programming patterns from ML. We did not even touch on that in Prolog here. But if you really enjoy Prolog, there are other languages similar to it that are declarative, that give you capabilities like this, but not quite in the way that Prolog does it, in this very logical way of doing things. And so if you're really interested in Prolog, there are several good books out there on it that I would definitely suggest reading. One of the better ones is Programming in Prolog. I would really suggest taking a look at that. It's a great book. I've read a vast majority of it a long time ago, so I'm a little rusty, but it covers a significant amount of interesting concepts. Anyway, so that's it for Prolog, and I'll see you all on Friday, tomorrow, and have a great evening, and I look forward to seeing you. Have a good day.